So good afternoon, everyone. Welcome back to Math 122 for the very last time. Well, I guess unless you count the final exam, that'll be the last time. But today's the last time that I'll be giving you instruction. So the plan for today's class is just to review for the final exam. So you can ask me any questions that you like. That could be as vague as I don't really understand Riemann sums, or as specific as please do this problem number 3 from this particular homework. So with that in mind, if you haven't prepared any questions yet, now's a good time to start thinking about some things you want to discuss. Otherwise, let me just remind you that the date of the final exam is May 2nd. So actually, let me write it down. And since we're doing a review, we can go dark mode today. So, final exam is in this room. May 2nd. Is it 4 p.m.? I think it's 4 p.m. Regarding assignments, today's the last day that you can get your quizzes or exams back from me. So if you're missing any, please stay after class, and I will give you them back. The only reason that I would still have your assignments is if you've missed some classes. You'd probably have to miss several classes for me to have not handed you back stuff. But if you need them and you are just watching the recording right now, then you can email me and come to my office. And that's how we can exchange papers. So one thing I want to comment on quickly is I just want to address everyone who has sent me an email or will send me an email about what grade do I need to get on the final exam in order to achieve X grade. It's all in the syllabus. If you look at the weights and the percentages of what the assignments are worth, what the quizzes are worth, what the exams are worth, and you can also make sure to incorporate this drop policy for the final exam, where the final exam can replace a low midterm grade in addition. Use a website. There are websites that will do it for you. Just Google weighted grade calculator, type in your grades and the percentages that they're worth, and then you can run the numbers and see the various different percentages that you could get or need to achieve on the final exam in order to get the grade that you want. And if you really need more help with that, then you can come to my office hours and we'll do it together in my office hours sometime next week. Which, by the way, my office hours next week are going to be the same as usual, but there will be no office hours on the day of the final exam. So that's May 2nd. I usually have Tuesday office hours. There will not be office hours on the day of the final exam. Any administrative questions, comments, or concerns before we jump into the review? All right. If not, then who's got some questions? Yeah, Abdullah?
Find unique antiderivative given the set point of x, 3 over x.
Sorry. Yeah. So little f of x is 3 over x.
Yeah, and f of 1.
Capital F of 1 is 9.
Yeah, I don't see that. I didn't see that in the assignment. I saw it last week on YouTube. So I saw on the YouTube, discussing it in the YouTube last week.
Yeah.
So I didn't see it in the assignment. Just wanted to,
The initial value problem. There's no initial value problems on the final assignment?
Not the same problem.
Not the same exact problem, but similar problems.
Yes.
Okay. So yeah, let's do this one together then. So this is an initial value problem, and they tell us to find the, and they use the word the, unique antiderivative. of f under this constraint. Okay, so we need to find an antiderivative of little f of x. So we need to think of a function whose derivative is 3 divided by x. Well, what we're trying to do here ultimately is something like the following. We want to do the indefinite integral, so no bounds because I'm looking for a function here, of little f of x dx, right? So in this case, we want to do the integral of 3 over x dx. So using the rule which says, the rule for linearity of integration, this tells us that we could rewrite the inside as 3 times 1 over x, and that's not linearity yet, but here it comes. Linearity says you can take any constant out of the function, out of the integral. Okay, you can take a constant out. So I do 3 times the integral of 1 over x dx. So now I need to think of a function whose derivative is 1 over x. And that function we learned in class is ln of the absolute value of x plus c, right? So we get 3 times ln x plus c. Okay, so this is the general antiderivative of little f of x. When I do an indefinite integral, so no bounds here, no a, no b, no 0 to 5, no nothing like that, just an indefinite integral, what I get as my answer is a collection of functions. So when I write this, what I'm referring to is a big bucket, and in my bucket I throw in the function 3 ln x, and I also throw in 3 ln x plus 1, and I also throw in 3 ln x plus 2 and plus anything, or minus anything, right? So this is a collection of functions, but I'm supposed to find the unique antiderivative. Okay, so the unique antiderivative means from my bucket I must select the specific one that they want. And they want the function which is in my bucket, i.e. is an antiderivative of little f, and this other constraint. It's the one in my bucket such that if you plug in 1 you get 9. So now I'm going to use the second constraint to identify what the unique antiderivative is in the following way. I know that f of 1 is what I would get if I plug in 1 into this function, whatever it might be. We don't know what c is, but we know if we plug in 1, what we would get is 3 times ln of the absolute value of 1 plus c. And that should be equal to, because of the constraint, this should be equal to 9. So this tells us essentially how to pick c in the right way. Okay, we're supposed to find the specific c, which is going to single out just one function from infinitely many. So if I see this equation, this is just a linear equation in c, so I can solve for c, right? So ln of absolute value of 1 is the same as just ln of 1, because the absolute value of something positive is just itself. And I have plus c is equal to 9. So nothing crazy going on here. I just need to know what is ln of 1. And if you forget how to do it, here's how you do it. You say y is equal to ln of 1, and then you raise both sides. You say e to the y, then it should be equal to e to the ln of 1, and these cancel to give you just 1. So I need the number y such that e to this number is equal to 1. What should y be? Yeah, y should be 0. So we did this in class on Tuesday, I think. We get 3 times 0 plus c is equal to 9, and therefore c is equal to 9. So the unique antiderivative for this one is the function 3 times ln absolute value of x plus 9. Can everyone still see? Is it too small? Okay. So The idea is if I have to find the unique antiderivative, the first thing I do is I find what do all of the antiderivatives look like. I know they all look like this, but I need to figure out which of them is the correct one. So I have this additional constraint, f of 1 equals 9. So I plug 1 into my generalized formula, and I know that that should be equal to 9. And this equation here can be used to identify what is our c value for our particular antiderivative. And now at the very end, my answer is just one function. Okay, so it's not a whole set of functions anymore. I took my set of functions and I grabbed the specific one which satisfies the constraint f of 1 is equal to 9. Okay? Any questions on this one?
Would that have the little antiderivative, the hash mark, like next to the f? Like this, I don't know,
Like here, like a prime?
Yeah.
Okay, so we wouldn't use a prime here because in this case what we're saying really is that what would capital F prime be? This is f. Capital F prime would be doing the derivative of this function, which the 9 would go away, right? And we'd be left with 3 times whatever the derivative of ln x is, which is 3 times 1 over x, which is 3 over x. The whole point of this is that the derivative of this function is 3 over x, which is what we started with. So we're going in the opposite direction. We're trying to find the function whose derivative is what we started with. That's why we call it antiderivative. Good question. Any other questions? All right, so all of the antiderivative problems, all the initial value problems, so that's what IVP stands for, is initial value problem. The initial value in this case is f of 1 equals 9, right? So all of the initial value problems have the same form. They give you the function, you have to find the antiderivative, and you have to use that constraint to figure out c, okay? So the first thing we do is just find the antiderivative. So we only know how to do antiderivatives for like 3 different functions, okay? We got like power rule, e to the kx rule, and ln x rule. That's all we know how to do antiderivatives for. So as long as you know those 3, and you know how to do this process where you plug in something and set it equal to something else, solve for c, then you can get your final answer like this. So all that this amounted to was finding an antiderivative and then determining the constant. All right. Should we move on to something else or more questions on that one? Okay, let's do something else. So, Aiden got one?
That's from the last test. G of x equals x times e to the negative 2x.
And it's find and classify?
Yes.
The critical points. Okay, so this one was on our second exam. So this is a problem where we need to find and classify the critical points. And what we learned in chapter 4 was that we have a critical point anytime that the derivative is equal to 0. So let's go ahead and find the derivative first. So to find the derivative, what rule am I going to need to use? What rules? Yeah, product rule, because I have a product of 2 functions here. The first function being x and the second function being e to the minus 2x. And then I'm also going to need to use the e to the kx rule to do the derivative of this guy. But what we need to remember when we're doing the derivative of a product is it's not just going to be the derivatives multiplied together, okay? This is what some people thought we should do, is we should just take the derivative of each of them and multiply them. But we actually can't do that. We need to use the product rule. The product rule tells us the following. It tells us that if you have 2 functions and you do the derivative, then you're going to get f prime g plus f g prime. So what's much more important than the letters here is what is happening underneath the hood. we're taking two functions being multiplied. The answer is you do the derivative of the first function and you leave the second one alone, and then you swap the roles. You leave the first function alone and do the derivative of the second one. Okay, so in this case, you could say my f is like my x and my g is like my e to the minus 2x. So first off, I need to do f prime g. So that's derivative of x, which is 1, multiplied with, and I'm going to leave the second part alone. So just e to the minus 2x. And then a plus sign. And now I need to do f g prime. So x gets left alone, and I need to multiply that with the derivative of e to the minus 2x, which via the e to the kx rule is minus 2 e to the minus 2x. And now I can simplify just a little bit. This is e to the minus 2x plus, no, minus 2x e to the minus 2x. And my goal was to set this equal to 0 and determine what x values will cause this equation to be 0. Okay, in order to do that, what we can do is notice that there's a GCF, right? There's a greatest common factor between these two terms. So I can pull out an e to the minus 2x, and left inside, what should I have left inside after I pull out e to the minus 2x? Yeah, Leah's got it exactly right. It's 1 minus 2x. So I'm doing like a reverse distribution here, right? If you were to distribute e to the minus 2x onto both of these guys, then you would recover what you just had. Okay, so pulling out a GCF is like, you can think of it as anti-distributing, okay? So we pull out e to the minus 2x, and we set this equal to 0. Now, the zero product property tells us that if I have one number times another number is equal to 0, then either the first number, a, is equal to 0, or b is equal to 0. That's what the zero product property says, which is why when we do factoring, we set both of the factors equal to 0. So in this case, I can set them both equal to 0. E to the minus 2x equals to 0, and 1 minus 2x is equal to 0. So the one on the right I can solve easily. I just get x is equal to 1/2. And what about this one? That one's kind of confusing. What do we think about this one? E to the minus 2x equals 0. You could try to do ln. Owen? Yeah, this is a function which is never 0, which is characterized by saying that it has an asymptote at y equals to 0. So you can look at this in two ways. First of all, this will never be 0. Okay? Never true. Here's how you can see it. Well, first of all, you might think, well, what if I plug in 0? Well, if you plug in 0, then you get e to the 0, which is 1, which is not 0. Okay? So 0 is off the table. But moreover, if x is positive, then this will be something like 1 over e to the 2 times x, right? So if x is positive, then you're just dividing 1 by a positive number that will never be 0. Or if x is negative, then this will be like, so if x is negative, then this will look like e to the minus 2x. This will be a positive number because x is negative. So you're taking e raised to some positive power. So no matter what you plug in for this power, you're always going to get a positive number. Okay? You're always going to get a positive number. Another way to visualize that is to recall back when we graphed exponential functions, they all have one thing in common, which is, okay, for this one, it's exponential decay, so I'm going to draw a shape which looks like this. But all exponential functions have the horizontal asymptote, which is y equals 0, which means they get closer, they can get as close to 0 as they want, but crucially, never touch it. Okay, that's what an asymptote is. So you're exactly right, Owen. So this is never equal to 0, so I just forget about this. So I have one critical point. That's when x is equal to 1/2. So I still need to classify it. So to classify it, I can do two things. I could use the first derivative test. So if I use the first derivative test, I draw a number line, and then I pick two test points. So I'm going to pick 0 and 1, because those are easy to plug in. And since I'm doing the first derivative test, what I want to do is I want to take 0 and 1, which are my test points, and plug them into the first derivative. So g prime of 0 would be what I get when I plug in 0 into this function, right? Which would be e to the 0 times 1 minus 0, which is 1 times 1, which is 1, which is a positive number. So my function is increasing up until 1/2. And next up we have g prime of 1 would be e to the 1 times 1 minus 2, which would be e times negative 1, which would be negative e, which is a negative number. So then my function is decreasing. So this tells me that x equals 1/2 corresponds to a local maximum. And that's my only critical point. So at this stage, I would be done if I used the first derivative test. But there's also another option that we could have used. We could have used the second derivative test as well. I would prefer not to use the second derivative test for this function, because if I use the second derivative test, I need to compute the second derivative, which means I need to define the derivative of this function, which is again going to involve a second application of the product rule, which I can go ahead and do, but it will be annoying, and you'll see how much more work it is. So remember, g prime is e to the minus 2x times 1 minus 2x. So then g double prime, I need to use the product rule again. So I have two functions being multiplied. The first thing I do is the derivative of the first one and leave 1 minus 2x alone. And then I add, and now I need to leave the first function alone and do the derivative of the second one, which is just negative 2. So that gives me, all told, negative 2 e to the minus 2x, I'm distributing, plus 4x e to the minus 2x minus 2e to the minus 2x, which is 4x e to the minus 2x minus 4e to the minus 2x, which is which is that. Probably just leave it there. And then what do I need to do? I need to check what is g double prime of 1/2. So I need to go ahead and plug in 1/2 here. So I get 4 times 1/2 times e to the negative 1 minus 4e to the negative 1, which is 2e to the negative 1 minus 4e to the negative 1, which is negative 2e to the negative 1, which is negative 2 divided by e, which is a negative number, which is all to say that the function is concave down, which implies x equals 1/2 corresponds to a local max. Okay, so you can go ahead and use the second derivative test if you want, but like I said previously, there's some situations where the second derivative test is significantly easier, and there's some situations where it's significantly harder. And in this case, it turns out to be a little bit harder. And your next natural question would be, Tom, how do I know which one is going to be harder before I start? And that's something that, again, you'll pick up the more practice that you have. But for me, the crucial identifying fact was I looked at this and I said, I don't want to do another derivative of that. That's going to get messy, because I can already see it's already become significantly more messy from using the product rule, and I'm going to have to use the product rule again, and that's going to be annoying. So that's why I think that when I see this, my first instinct is to use the first derivative test and not the second derivative test. Okay, so that's, I think, the full story on this exam problem. So are there any questions about any of it? Yeah.
So e to the 0 and 1 minus 0, right? The g prime of 0.
Oh, yes. So, yeah, here?
So it's 1 minus 0, right?
Yeah.
So y down is 1 minus 2, and it's not 1 minus 1.
So what I'm doing here is I'm trying to compute g prime of 0, which means what I'm trying to do is plug in 0 into the g prime function. So let me bring your attention up to here. So this is the derivative, right? So if I'm doing g prime of 0, what I'm trying to do is I'm going to put in 0 for x here, and I'm going to put in 0 for x here, right? So in this case, it becomes e to the 0, since negative 2 times 0 is 0. And then this part becomes 1 minus 0, because 1 minus 2 times 0 is the same as 1 minus 0. Yeah?
So but down one, you said 1 minus 2. You didn't do like 1 minus 1.
Right. So the reason is I'm plugging in 1 for x. So in this case, oh, and I made a mistake here. This should be e to the, this should have been e to the minus 2, right?
All right.
So, but the point is, I'm plugging in 1 here, and I'm plugging in 1 here. So when I plug in 1 here, this becomes 1 minus 2 times 1, which is the same as 1 minus 2. Does that make sense? Answer your question completely? Okay, cool. Any other questions on this one? So product rule, finding critical points, classifying critical points using first or second derivative test. All right, then let's move on to the next one. Yeah, Andon.
Can you do the Riemann sums?
Sure. You got a specific one in mind, or you want me to pick one?
No, sir. You just like.
Can I pick one? Yeah. Let's do this one. This should be fun. We can make this, we can turn this into a Riemann sum problem. Actually, maybe that's too complicated. Let's do something else. Okay, let's do this one. Using a right Riemann sum. Actually, why don't we do a left Riemann sum, since we did a right Riemann sum on our exam. So we'll do a left Riemann sum with n equals 6 rectangles. Okay, so we're going to find the area which is underneath this function, actually which is between this function and the x-axis. Ooh, let me think about that for a second. Yeah, which is between this function and the x-axis on the interval from 0 to 3. Okay, so the first thing that would probably be helpful, if you can do it, would be to try to draw a sketch of what is going on with this function. Okay, it would be to try to draw a sketch of what is going on with this function. So this isn't necessary, okay, in order to apply the theory, but I'm going to show it to you anyways, just to help you see how helpful it is to have a picture. So we can make a picture of this function using tools which are from like algebra or pre-calculus, which tell us, well, how do we graph a function like x cubed minus x? Well, we could rewrite x cubed minus x as x times x squared minus 1, couldn't we? And that could be rewritten as, in factored form, as x times x minus 1 times x plus 1. And if we set that equal to 0, we can find out where this function touches the x-axis, which in particular is going to touch at positive 1, at 0, and at negative 1. So we know this is a cubic function. It touches the x-axis at 1, 0, and negative 1. And we also know that it has a positive leading coefficient. So positive leading coefficient for a cubic function means that it will look like this, as opposed to a negative leading coefficient, which would mean that it would look like this. So we know that our picture should look like this, and it should touch the x-axis at these 3 points. So let's draw a basic cubic function which satisfies these properties. Could look something like the following. Okay? Could look like the following. And we are supposed to find the total area bounded by this function and the x-axis between 0 and 3. So let's draw a picture of what we want. So here's 1, so 2 is out here, and then 3 is even further out. So I should even make my picture bigger, probably. So what we are after, at the end of the day, is this area plus this area. Okay, so these are the two areas that we want to find. And I want to note, okay, that this is different, okay? This is different from trying to approximate the integral from 0 to 3 of little f of x dx. What would this represent? This would represent taking, so let's call the area above A, and let's call the area below B, B for below. So what would the integral from 0 to 3 of f of x dx be? We would get A, which is the area above the x-axis, and we would subtract the area which is beneath if we were doing an integral. Okay, but we're not doing an integral here. There is a difference between doing an integral and finding the quote-unquote total area between this function and the x-axis. For the total area between this function and the x-axis, what we want actually is not a minus b, but a plus b. Okay, a plus b for this particular problem. Okay, because we're counting area, all of the area as positive in this case. Okay, so slight difference between an integral and finding the quote-unquote total area. But let's see how we would do this using a left Riemann sum with n equals 6 rectangles. Well, the first thing that I would do is I would determine what is my delta x. And my delta x is always going to be b minus a over n. And b is always the endpoint on the right, and a is the endpoint on the left. So those are going to be 3 and 0, respectively. And n is the number of rectangles, and they tell us n should be 6. So in this case, delta x is going to be equal to 1/2. Okay? So the width of each rectangle should be 1/2. So let me update my drawing just a little bit here. So here is 1/2. Here is 1. Here is 3/2. Here is 2. Here is 5/2. And then finally there's 3. So what I need to do is find rectangles, and the height of each rectangle should be the height of the function on the left side of each subinterval. So on the left side, for the first rectangle, so I will draw my rectangles with, I'm running out of colors. I'll draw my rectangles with green. First rectangle has height 0. Second rectangle looks like the following. Third rectangle, again, has height 0, because that's the height of the function on the left side of this interval. Then the next rectangle will have this height shown here. The next rectangle will have this height shown here. And the final rectangle will have height, which is the height of the function on the left side of the final subinterval. So altogether, we have 6 subintervals, 1, 2, 3, 4, 5, 6. But 2 of them are actually kind of negligible, right? So we're actually going to add up the area of 4 rectangles. So we would say that the area A is approximately equal to 1/2 times 0 plus 1/2 times f of 3/2. In fact, why don't I swap 0 for f of 1? And then plus 1/2 times f of 2 plus 1/2 times f of 5/2. Which for this problem is going to mean 1/2 times 0 plus 1/2 times f of 3/2. So to do f of 3/2, what do I need? I need 3/2 cubed minus 3/2. So that's 27 over 8 minus 3/2, which is 27 over 8 minus multiply top and bottom by 4, 12 over 8. So this is 15 over 8 plus 1/2 times f of 2. Well, if I plug in 2, then I get 2 cubed minus 2, which is 8, minus 2, which is 6, plus 1/2 times, now I need to do 5/2. So for 5/2, it's going to be 125 over 8 minus 5 over 2, which multiply top and bottom by 4, we get 125 over 8 minus 20 over 8, which gives me 105 over 8. So clean it up a little bit. This is 15/16 plus 6/2 plus 105/16, which is 120/16 plus, and I'm going to replace 6/2 by multiplying the top and bottom by 8. 48/16 equals 168/16. Oh, this is more math than I was hoping to do. I think 4 goes into both, right? What do we get when we do 168/16? Okay, thanks. So 10.5, if I was using a calculator, which you wouldn't need to. So don't worry, I won't make a problem this complicated on the exam. But this is basically how we find the area, the approximated area of these rectangles, which represent the area of A. And for B is just going to be approximately equal to the area of this one little rectangle, which is just 1/2, which is the width of that rectangle, times the height of that rectangle, which should be 1/2 cubed minus 1/2, which is 1/2 times 1/8 minus 1/2, which is 1/8 minus 4/8, which is 3/8. Which is -3/16. But we have to remember something here, which is that B is an area. If we're measuring area, even though the height of the function is negative, when we're talking about a length, we're referring to something which is inherently positive. So in this case, we want to make sure that our end result should be positive. So we get 3/16 for B. So if you were counting this area as negative, as you would be in the case of integral from 0 to 3 of f of x dx, then you would do a minus b. So you would take 10.5 minus 3/16. But since we're counting total area, we would do 10.5 plus 3/16. And that would be our final answer. Okay, how do we feel about that one? Do we have any questions on this one? Okay, so I know there was a lot of calculating there, right? But it's all just multiplying fractions. The idea that I want to communicate by doing this example is the following. First of all, the idea that having a picture is incredibly useful. Okay, so having a picture is incredibly useful. And what's next? When we do a Riemann sum, we need to determine what is the width of every rectangle, which is done using the formula delta x equals b minus a over n. So next up, we just need to make our Riemann sum, okay, by multiplying the width, which is the same for all of them, times whatever is the height of each rectangle. And the height of each rectangle will be determined based on whether you are doing a left Riemann sum or a right Riemann sum. Okay, whether you're doing a left Riemann sum or a right Riemann sum. Okay, any questions on that one before we move on to something else? Let's have some thumbs. I want thumbs up if you would get full points on this problem on the final exam, and thumbs down if you would get no points, and then somewhere in between if somewhere in between. Just try to be honest with me. I just want to get an idea here. Real high, please. Really high. Okay. I'm seeing more than a few thumbs sideways or down, which I gather based on the looks on your faces. So maybe let's do another example of Riemann sums. Maybe something a little bit easier. Okay. Okay, this one I think is easier. So I'm going to go through this one without drawing the picture. Okay? It will be a lot easier if you can draw the picture, but I know not everybody feels that comfortable looking at a function and knowing what the graph should look like. So I want to go through one where we just apply the formula directly. Okay, we just apply the formula directly. All right. So here's how I'm going to start out. They tell me that I should use a left Riemann sum. And I was a good calculus student, so when Tom told me about left Riemann sums, I wrote down the definition of a Riemann sum, left Riemann sum on a note card, and then I memorized it, so I can at least regurgitate the following formula. Oops. And even I'm regurgitating it incorrectly. I equals 0 to n minus 1 of delta x times f of a plus I times delta x. Okay, I'm not trying to disparage you if you didn't memorize this formula. In fact, I think it's totally fine if you didn't memorize this formula as long as you know like how the process intuitively works, okay? When we're just counting up the areas of rectangles, okay? As long as you can figure out the width of those rectangles, how many there are, and the height of each of those rectangles, you don't need the formula. But some people like to have the formula, so let's work from there and see if we can get the answer without drawing a picture of this function. Okay, so in order to complete this, I just need to figure out what is A and what is delta x. And that's pretty much it. Okay? So A comes straight away from looking at my integral here. The integral goes from 0 to 8. So therefore A should be 0 and B should be 8. Now I still need that formula for delta x, which remember delta x was equal to b minus a over n. Okay, b minus a over n. So using that formula, I get delta x equals to 8 minus 0 over 4.
Over 3, innit? Because n minus 1.
The n minus 1 is going to come in the sum, but right now I'm just working with this formula. So this formula, we have just n. We're going to get to n minus 1 in a second, though. So what does this tell us? This tells us that the width of each rectangle should be 2. Okay, in your mind, even if you don't know what 1 over 2x looks like, you know what you're doing is whatever this function is, you're going from 0 up to 8, and you're using 4 rectangles. If you go from 0 up to 8 and you use 4 rectangles, they each need to be 2 wide. Right? They need to be 2 units wide. Okay, but we said we're not going to draw pictures, so that's why I did it with the red laser. Okay, so let's apply the formula now. So sum should go from I equals 0 to n minus 1, which, as you say, Abdullah, should be 3. Now I replace delta x by whatever it is equal to, which in this case it's 2. So I get 2 times f of, what's a? A is 0. So I put 0 where a is, and then I have plus I times delta x, which is again 2. And I can clean that up just a tiny bit more because 0 plus anything is just whatever you add to 0. Whatever you add to 0. So we get just 2 times f of 2I. And now I can go ahead and perform the sum. So the way I perform the sum is now I'm going to not write this summation notation anymore. I'm actually going to do the sum, which this notation says let I be 0, and then 1, and then 2, and then finally 3, and then add up all of the bits. So the first term will be 2 times f of 2 times 0. And then we get a plus. So this was the term for I equals 1. So this is I equals 0. And then the next term will be for I equals 1. So now we're going to let I be 1, and we get 2 times f of 2 times 1. Then plus 2 times f of 2 times 2. And then plus 2 times f of 2 times 3. And that's where I'm going to stop. I'm going to stop going once I get to I equals 3, because the sum tells me 3 is the last one you should do by putting this 3 on top of the sigma. Are we okay up to now? Any questions up to this point? Okay, then let's go ahead and finish it off. In order to do that, I just have to plug in, right? So this becomes 2 times f of 0, because 2 times 0 is 0. So I just want to plug 0 into this function. Oh, crap. Oh, we should have foreseen this happening. So I can't use a left-hand sum here, can I? Oh, why did this problem have to be written like this? Who? This was, okay, here's what we're going to do. And I apologize for not catching this sooner. We're going to replace the bounds. Instead of integral from 0 to 8, we're going to do integral from 2 to 10. So let me go through how that's going to change this. A is now 2 and B is now 10. But it's not going to change delta x at all, because when we do b minus a over 4, we're going to get 10 minus 2. Over 4, which is 8 over 4, which is 2 still. So the only thing this is going to change for our sum is that a isn't going to be 0. A is instead going to be 2. And we're not going to be able to have such nice simplification. Okay, instead we're going to get the following. We're going to get, again, first I will be 0, so we get 2 times f of 2 plus 0 times 2. So this is the I is equal to 1 case. Sorry, 0 case. Okay, I'm very sorry about having to change this problem on the fly. Are we all okay up to now? Do we need a little more time to catch up writing and erasing? Okay. All right, so now we need the other terms of the sum, which will be 2 times f of 2 plus 1 times 2 plus 2 times f of 2 plus 2 times 2. And then the last term will be 2 times f of 2 plus 3 times 2. And that's where I'm going to stop, because the last one is when I is equal to 3. So now we just need to plug in. So we get, well, let's simplify just a little bit. This is 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6 plus 2 times f of 8. So plugging in, I get 2 times 1 over 4 plus 2 times 1 over 8 plus 2 times 1 over 12 plus 2 times 1 over 16, which is 2 over 4 plus 2 over 8 plus 2 over 12 plus 2 over 16 is 1/2 plus 1/4 plus 1/6 plus 1/8, which is 4 plus 2. We'll have to put it all over 12. We'll have to put it all over 12. So this will be 6 over 12 plus 3 over 12 plus 2 over 12. Oh no, we got to go all the way up to 24, don't we? Jesus. This is just a disaster of a problem. Okay, so what do we want? 12 over 24 plus 6 over 24 plus so plus 4 over 24. I'm just thinking that this is going to be too much. Plus 3 over 24. Yeah, so you're right. Okay, so 12 plus 6 is 18, plus 4 is 22, plus 3 is 25. Okay, so minus a lot of adding fractions, which I will not make you do on the final exam. The first part is essentially following this formula. Okay, so it's entirely possible to do this without drawing the picture. Okay, so for those of you who would prefer not to draw the picture, do we have any thoughts on this or any questions on this process of how we just plug and chug with the formula? Okay, then follow-up question, would anyone like to see me draw the picture to illustrate what's happening here? Be brave. Ask for it if you want to see it. Okay, it doesn't seem like anyone wants me to draw the picture, so I won't. Are you sure?
Please.
Okay, thank you. I was waiting for somebody to ask me. Okay. Here's what the picture looks like. 1 over 2x has an asymptote at 0, which is why we weren't able to plug in 0, by the way. So if we go from 2 up to 10, so here's 4, here's 6, here's 8, and then 10. So maybe I put 10 a little bit too far to the right. So what are we doing? We're taking a Riemann sum with 4 rectangles. So I put 2, 4, 6, 8, and 10 on here as a way of subdividing the region from 2 to 10 into 4 equal intervals. And then I'm doing a left-hand sum. So I'm going to choose the width of each rectangle to be 2 and the height of each rectangle to be the height of the function on the left side of the subinterval, where I'll extend it to the right. So at the end of the day, I get rectangles which look like the following. So again, I think if you can draw this picture, you're going to have an advantage probably over people who don't draw the picture. Because once you see this, it's clear that this height here is just f of 2, right? And this height here is f of 4, and this height here is f of 6, and the last height here is f of 8. So if you draw the picture, you don't even need to remember the formula. You just do 2 times f of 2 plus f of 4 plus f of 6 plus f of 8. And then you're done. So I think if you can draw the picture, it will make your life a lot easier. Okay? Oh yeah, you're most welcome. Thank you for asking me to draw it, because I wanted to in my heart.
I can tell you.
Thank you. Okay, so any questions, final questions on Riemann sums before we move on to something different? Yeah.
Can you show me how you would have drawn it if it was a right-hand sum?
Sure. If it was a right-hand sum, the only thing that would change is for the first rectangle, I'm considering the first like I know that this is going to be where the rectangle is. It's like in here. And I just need to decide how tall should it be, right? So in order to decide how tall it should be with a left Riemann sum, what we say is we look at this interval and we just ask how tall is the function on the left side of that interval. So I draw a little L shape like this, L for left. For a right-hand sum, I choose the height to be the height of the function on the right side of the subinterval. So the difference would be that you would get rectangles which look like this. Instead. Okay, so let's wrap up Riemann sums. So who's got something else that they want to discuss? Maybe something from like yeah.
On the final homework assignment,
Okay.
question number 9.
Yeah, if you could read it to me, that'd be good. Yep.
It's a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when T equals 0.
Okay.
And then it says the coffee's temperature is changing at a rate of it's R of T equals -7 e to the -0.3 T. And it's degrees Celsius per minute with T in minutes. And it says estimate the temperature when T is 18.
When T is what?
15.
Okay. So this one requires a little bit of connecting like basically two concepts. Or maybe 3 concepts from like the last couple weeks of class. So this really is like a sort of a culminative thing, okay, which is going to help us to understand, this type of physical phenomena. So, okay, what do we have? We have a cup of coffee is currently 90 degrees, okay? So if we had a function t, which was a function of time, which describes the temperature at time t, then you would agree with me that t of 0 is 90. Yes? And you would agree with me also that this question is asking you, what is t of 15? Right? So they're asking us a question about a quantity, and they give us a function which tells us how that quantity changes in time. So can anyone summarize what is the relationship between the function t of t and the function r of t? Yeah.
Is R of t the derivative?
Exactly right. R of t is the derivative of capital T of t, right? So we have another relation. T prime of t is R of t. Okay, T prime of t is R of t. So now that we're at this stage, right, our goal is to find what is t of 15. But the problem is we don't have a function. We don't have a function for t. If we did, we could just plug in 15 and we would be done, right? So in order to help us answer this question, we need to know what is t of t. If we knew what t of t was, then we could plug in 15 and we'd be done, right? So what do I know about this function t of t? I know two things. I know that its derivative is r. That's thing number one. And thing number two that I know, t of 0 is 90. So this is going back to actually the first question that we had today, which was the initial value problem, right? How do I find the unique antiderivative? That will be this function t of t, will be the unique antiderivative of r subject to this additional constraint. You see what I mean? Okay, so let's go ahead and formulate this as another question. So a good skill to have when you're doing math, especially if you're doing word problems, is to be able to translate a word problem into the type of math problem that you're used to doing. So really what we're saying is find the unique antiderivative of r of t equals -7 e to the -0.3 t such that that function evaluated at 0 is equal to 90. Okay, find the unique antiderivative, why don't I call that antiderivative t of t, of r of t, such that t of 0 is equal to 90. And now we're back to basically the same exact kind of question that we answered at the start of the class, but it'll be good to do another example. So this is what we call an initial value problem, right? Because we have the initial value of the function, and we want to know what is the function itself. Okay, so let's solve this problem. So to do this, what I need to do is find out what is the integral of r of t dt, which is the integral of -7 e to the -0.3 t dt, which by the linearity I can pull the -7 out front. So I get negative 7 times the integral of e to the negative 0.3 t dt. And now what rule am I going to need to use to do the antiderivative of this? Yeah, the e to the kx rule. But remember, we're doing an antiderivative here. So I'm going to not multiply by k. I'm going to divide by k. Since I'm going the opposite direction, I'm doing an antiderivative. So here I'm going to write negative 7 stays, and now we have e to the negative 0.3 t, and also I lost a dot, didn't I? 0.7, right? Was it 7 e to the 0.3 t, or is it negative? Or is it 0.7?
It's negative.
It's negative 7? Okay, so I'm just losing my mind. Okay, so, and then divide by negative 0.3, right? Plus c. Okay, plus c. And this is our t of t. And now we use the second piece, which says that t of 0, which is what we would get if we did negative 7 times e to the 0 over negative 0.3. And if we add that to c, we should get 90. So therefore, c should be equal to 90 minus actually this makes a plus, so it should be 90 minus 7 over 0.3. So what is 7 over 0.3? Okay, so c is something like, you said 23, so like this is 113.3 repeating. So all told, our function t of t is the function negative 7 times e to the negative 0.3 t over negative 0.3 plus 113.3. What am I doing? We're subtracting. Jesus Christ, I'm making so many mistakes today. We subtract 23.3 from this thing, we get 67.7 repeating. So 67.7. Sorry. Jesus Christ. You know, when it rains, it pours. Okay. So altogether, we now have the function t of t. So we're just one step away from the finish line at this point. We found the unique antiderivative to r of t. So all that's left to do is answer the question, what is the temperature when t is 15? Well, the temperature when t is equal to 15 is what I get when I plug in 15 into this function. So t of 15 should be equal to minus 7 e to the minus 0.3 times 15 over negative 0.3 plus 66.7. And that would be my final answer for that one. Okay, so before you leave, I have 3 office hours next week, okay? 10 to 12 on Tuesday in the Math Tutoring Center, 3 to 4 in my office on Wednesday, and then on Thursday, 11:30 to 1 in my office as usual. So please come. That'll be the best time to study for the exam. All right, good luck.